graph the function 1 over 3 to the x power plus 1. Plot at least 4 points, including at least one negative input quantity. So here, this is actually negative 1 over 3 to the entire x power. So when we create a table, input quantity and output quantity, we plug x, which means we're going to raise 1/3, 1 over 3 to the x power. So let's plug -1. Then I get 1 over 3 to the -1 power plus 1. And this -1 power is the same thing as 1 over entire thing 1 over 3 to the positive power. That's what negative exponent means, right? Plus 1, which gives me 1 over 3 to the raised 1 power is 1 over 3. And 1 over 3 is same thing as 1 times 3 over 1. Dividing by fraction is same thing as multiplying reciprocal, which gives me 3. So I have 3 plus 1, which is 4. So that means that when x is 1, y is 4. So let's actually plot this one at a time as we find the points. So here, when x is -1, y is 4. 1, 2, 3, 4 right here. So let's find more points. Now let's try 0. 1/3 to the 0 power plus 1. Anything to 0 power is 1. So we actually have 1 plus 1, which is 2. So when x is 0, y is 2. When x is 0, y is 2. This point right here. Let's plug 1. And I have 1 over 3 to the 1 power plus 1, which is 1 over 3 plus 1. In order to divide a fraction, in order to add fraction to non-fraction, we need to have a common denominator. So 1 over 3 plus 3 over 3, because 1 is the same thing as 3 over 3. We'll get 4 over 3. So when x is 1, y is 4 over 3. When x is 1, y is 4 over 3. Now 4 over 3 is 1 and 1/3, right? So we can go 1 and go a little more than 1. So somewhere around here. Okay. Let's put one more point. There's at least 4 points, right? More the better, of course, because we can be more precise. But 4 is enough to see the trend. 1 over 3, second power plus 1. Now this is 1 square over 3 square, which is 9, plus 1, which is 1 over 9 plus 9 over 9, which is 10 over 9. Okay, so we have when x is 2, y is 10 over 9. When x is 2, is 10 over 9. Now 10 over 9 is smaller than 4 over 3. Right? Or we can think as, well, I'm adding 1 over 9 to 1, where I'm adding 1 over 3 to 1. And 1 over 3 is bigger than 1 over 9, right? Therefore, this point should be below this green point. So 1 and 1/9 is just right above the 1. Okay. So we plot these 4 points. There's one other thing we have to think about. Here we actually have this plus 1, which means we have horizontal asymptote. Okay. So the reason is that if you look at this expression right here, 1 over 3 x plus 1, this right here can never be 0 nor a negative when we raise to x power. So smallest we can have is very small, 0.0001 plus 1. So it can be, this graph never can go below 1. So we have horizontal asymptote right here. Numerically, that should make sense because whatever this is very small. We can make it very small, but we add that to 1. So we can have maybe 1.001 when x is maybe 100. But it can never be less than 1. Because this value right here can never be 0 nor negative. So we connect these dots. The function is decreasing, of course, like this. And it goes like this, approaches forever. And it decreases forever. but it will never go below 1 or even go to 1. Okay. So this is the graph of this function right here. And horizontal asymptote, as you can see, is important. Right? And you can also test in more points if you want. If you plug 3 and 4, we'll always get a number slightly bigger than 1. It will decrease, but always get slightly less than 1. Sorry, greater than 1. Change each exponential expression to an equivalent involving logarithm expression. So this is saying that 10 raised to x give us t. Right? So when we write in log, we have log of base. In this case, base is 10. Okay. And when I raise that to x power, it gave me t. And the other side is just the exponent. So we can think as 10 raised to x power give us t, where when we look at log, we're looking at what exponent is necessary for 10 to get t. That exponent is x. We can think as 10 raised to x power gives us t. Also, log base 10, sometimes for 10 we don't use. We actually don't write 10. We don't have to write 10. So if you see log without any number, that's implied that this is 10 here. So these two are the same thing. Okay, so only for 10, we go basic log, we don't write 10. It's implied. So let's look at the next one. X to the t power gives us y minus 23. Okay, so first we write log again. Log, what is base? Base is the one they're being raised to, which is x. Okay, and inside here, we get the result of a raising power. Y minus 23 equals t. So again, log is saying that what exponent is necessary for x to get y minus 23. So x raised to t gives us this inside right here. Let's get to the next one. S raised to 3x, 3 minus x power give us k. So log base is s, and the result of raising power is k equals, the exponent itself is 3 minus x. So again, this is saying that s raised to 3 minus x power gives me k. Change each logarithm expression to an equivalent involving exponential. So this is saying that x raised to negative 11 gives us 30. X raised to negative 11 gives me 30. Now here, we can also think as the negative 11 is the necessary exponent for x to get 30. So again, all same thing saying a different way. So this is saying x raised to negative 11 power gives me 30. This one, t raised to t power gives me t plus 12. So t raised to t power gives me t plus 12. This one's ln of r. Now ln is a natural log, which is same thing as log base e. E is the base. So that's implied. When you see ln, the same thing as log base e of r equals negative 2. So then we look at here, this is saying that e raised to negative 2 give us r. E raised to negative 2 power gives us r. Okay. Evaluate log base 3 of 1 over 27. Now when we look at this, we know that evaluating this gives us an exponent. Let's call it t, a number. So this is asking you to find what t is. So when you look at log of something, with specific number, numerical values, we're finding an exponent. What exponent specifically? We're finding 3. What exponent is necessary for 3 to obtain 1 over 27? So essentially, 3 raised to what power gives me 1 over 27 is what I'm asking. So there are a few ways to do this, but I think one of the efficient way to doing is try to rewrite this in terms of 3 power. So 27 is the same thing as 3 to t raised 3 power. 3 to the second power is 9. 3 raised to 3 power is 27. So then 3 to the third power, same thing as 3 to the negative 3 power. So then t must be negative 3. So t is negative 3. So we can also say that log base 3, 1 over 27 equals negative 3. Okay. So it is okay to have a negative exponent, right? But inside of log cannot have negative nor 0. Something to keep in mind. Okay. Find the domain of follow functions. So when we find the domain, we're finding what x values can we not or can we have. Right? So remember, for log, we cannot have negative or 0 inside of log function. It's because this is saying that 4 raised to f of x gives us x plus 5, right? But anything to raise any power cannot give us negative. Right? Even if we raise to negative number, it gives us positive number, which is 1 over 9 in this case, right? Therefore, inside log function, the x should be such that whatever x is, it should always give us positive. So that means that x plus 5 must be always greater than 0. Not greater than equal to, strictly greater than 0. That means x has to be greater than negative 5 in this case. So that's the domain, right? So in interval notation, it's negative 5 to infinity, excluding negative 5. Okay. Let's look at this one. Natural log of x squared minus 4. Natural log is just a special type of log. The same rule apply here where inside cannot be 0 nor negative. Okay, so that means that x squared minus 4 must be greater than 0. Okay, so x squared must be greater than 4. So here we actually have two cases. When is x squared greater than 4? Well, first, we know when x is greater than 2. Right? When x is greater than 2, we'll have 2 squared is 4. So if I have 2.1 squared, for example, that's greater than 4. Or if I have 3, I have greater than 4. Also, though, we have x need to be less than negative 2. Because, for example, negative 3 squared is 9, which is greater than 4, right? Or negative 4 squared, 16, which is greater than 4. So on the number line, x has to be less than negative 2. X has to be greater than 2. So x has to be greater than 2 or less than negative 2. As long as those numbers we plug in here, inside will be positive. So let's write the domain in interval notation. Negative infinity to negative 2, union 2 to positive infinity. Because all we care about is not being negative, nor 0. It cannot be 0 either. And it will be 0 when we plug negative 2 and positive 2, right? But we're excluding negative 2 and positive 2 here. Solve the equation. So here it says log base 4 of x plus 5 equals 2. So if we can write in terms of log exponential expression, we should. So here we can rewrite this so that 4 raised to 2 power equals this. So 4 raised to 2 power gives us x plus 5. And just solve for x. 16 equals x plus 5. Subtract 5 both sides, we'll get 11 equals x. So x is 11. But then for log functions, it's very important to always check our answers. Can I plug 11 here and do I get positive number inside of log? It does, right? So we have to always check our answers. Sometimes you might not. So this works because 11 plus 5 is positive 16, right? But if one of the solution gives us negative or 0 inside of log, that is not part of the solution. So keep that in mind. Log base 3 of x plus 12 equals 2. So here we can rewrite if we can 3 raised to 2 power equals x plus 12. So 9 equals x plus 12. What is x? I subtract 12 both sides. X is negative 3. Now again, we have to check our answer. Can I plug negative 3 here? And this inside of log still stays positive. Well, negative 3 plus 12 is 9. It's positive, so that's okay. So this is a solution. So we always have to check solutions for log equations when we have a log in the given equation. Graph 5 to the x power and log base 5 of x. Plot at least 4 points equals at least one negative input quantity. So here we're actually going to make a table for this first, and maybe plot this first. And note that log base 5 is inverse of 5 to the x power. Those are inverse function. So let's see how those relationships look. So first, let's do f of x here, which is x and 5x. Right, so if it's negative 1, we'll get 5 to the negative 1 power, which is 1 over 5. When it's 0, anything to 0 power is 1. When it's 1, we get 5. When it's 2, we get 5 squared is 25. So let's plot these 4 points. So when it's negative 1, x is negative 1, it's 1 over 5. So it's 1 over 5 is small here, 1 over 5. When 0, it's 1. When it's 1, it's 5, so it's all the way here. When it's 2, it's 25, so it's really big, way above, right? So let's say just really high, maybe somewhere here. So if I connect these, and here is implied horizontal asymptote, right? We have implied horizontal asymptote of 0, because 5 to the x power cannot be less than 0. It can be very small, it can be very close to 0, like 1 over 5. Or if I plug negative 100, I have 1 over 5 to the 100 power, which is a very small number. So this is this graph right here. Okay. So at 2, yeah, it's 25. But what we important is the trend of this increase very rapidly. Right? So that's the f of x function. Let's graph this inverse function. So f inverse. And because they're inverse, the domain and range switch. So what I mean by that is if you look at here, when x is negative 1, the output is 1 over 5, right? So for this quantity here, it will be switched here. So let me write that. What I'm talking about is we switch domain range. So when x is 1 over 5 for this function, the output is negative 1. And also we look at this right here. This means that for inverse function, domain, these are switched. When input is 1, output is 0. Same here. 5, 1, 25, 2. So let's plot these 4 points for f inverse or log base 5. That's what we're graphing, right? Log base 5 of x. So when x is negative 1, 1 over 5. Oh, I'm sorry, when x is 1 over 5, which is right here, somewhere here, is negative 1. So somewhere here. When x is 1 is 0. When x is 5, 1, 2, 3, 4, 5, y is 1. Now when x is 25, we'll have somewhere all the way here, maybe like really big, is 2. Right? So let's say somewhere here. Well, 3 is enough to actually see the trend, right? So we're gonna graph it this way. Oh, let me do it no longer. It goes this way, and it goes on this way. This will not also, it has a vertical asymptote of 0 here, so we'll graph like this. Now, these are inverse functions to each other. Graphically, what that means is that we have a y equals x line, diagonal line, y equals x. And if I were to rotate this blue graph, I'll get this red one, right, along the x-axis. Sorry, along the y equals x line. If I rotate this blue graph, or if I reflect along this diagonal line, I get the red one, and vice versa. That's what it means to have an inverse function, right? And when we actually rotate it, this horizontal asymptote also rotates together for blue one. So that's why we have a vertical asymptote for the red function, the log base 5x. Okay. And again, this should make sense. This is saying that log 5 of x, right? The inside cannot be negative or 0. So that's why we have this vertical asymptote for this function, the log base 5 function, because x always has to be greater than 0 when we plug in here. Graph 1 over 4, this is 1 over 4 to the entire x power, and inverse function of that, which is log base 1 over 4 x. Actually, let me rewrite that like this. So let's graph this first, then we're going to invert this function to graph this one, because we need to understand these are inverse functions to each other. So let's graph f of x first. Create a table. So plug at least one negative quantity, so negative 1. If I plug negative 1, I get 1 over 4 to negative 1, which is 1 over 1 over 4, which is 4. So negative 1, comma 4. If I plug 0, I get 1. Anything 0 power is 1. If I plug 1, I get 1 over 4. If I plug 2, I get 1 over 16. So let's plot these first. Increase one at a time. So when x is negative 1, y is 4. When x is 0, y is 1. When x is 1, y is 1 over 4. So here's halfway, maybe half of halfway right here. When x is 2, it's even smaller, right? 1 over 6 is barely above the x-axis. So I plot these. This graph right here. Again, here's a horizontal asymptote, because 1 over 4x power cannot be less than 0, or it cannot equal to 0 either, right? It'll always be greater than 0. That's why we have horizontal asymptote. Right? So we plot these 4 points. So then let's invert this so we can graph f inverse, which is log base 1 over 4 of x. So that means that, look at this pair, negative 1 comma 4. For inverse function, we switch domain and range. So it becomes 4 comma negative 1. Becomes 1 comma 0. 1 over 4 comma 1. 1 over 16 comma 2. Okay. So let's plot this graph. When x is 4, y is negative 1. So right here. When x is 1, y is 0. So this one stays here. When x is 1 over 4, very small bit, it's halfway, 1 over 4 here. When x is 1 over 4, y is 1. So somewhere here. And when x is 1 over 16, very close to 0, is 2. So maybe somewhere here. So we have graph looks something like this. Okay. And here is actually vertical asymptote, because inside of log, right? Inside of log always have to be greater than 0, right? So we can only plug number of greater than 0. So make sure you draw it a little better. Here's the red graph, log base 1/4, and below one is 1/4 to the x power. So these two are inverse to each other. That means that they can reflect along y equals x line. So if I have y equals x line right here, here's y equals x. If I reflect this blue graph, or if I rotate along the y equals x line, I get this red one, and vice versa. Right? So if I rotate this, 1/4 to the x power, you can imagine like 3D, rotate along the y equals x line, and then we'll get this red line. Or we can, if you rotate red one along this y equals x, or reflect y equals x, then we'll get this blue line. Yeah, so these two functions are inverse to each other because they're can be reflected along the y equals x line.